The syllabus of class 12 for mapping of functions is one-to-one and onto functions, composite functions, inverse of a function. These are the things that we need to know in class 12. Okay. So before we begin, I need the concept of the function. Although you have done it in class 11, let us brush up on our knowledge. Okay. Now, what is function? Function is a special type of a relation. Function is nothing but a type of a relation. You can say function is also a relation. Okay. But then, why is it a special type of a relation? Because it includes some important things. Okay. From the definition, you can say that a function relates each element of x to a unique element of y. For example, you can see over here, in this particular example, in x there are 3 elements 1, 2 and 3, and in y there are 3 elements a, b and c. You can see 1 is related to a, 3 is related to c, 2 is not related, b is not related to anything. Yes, but since 1 is related to a and 3 is related to c, I will say that there exists a relation from x to y. Correct? But this is not a function. Why do I say that? Because in the definition it says that a function relates each element of x to a unique element of y. Understand the word each. That means every element in x must be related to an element in y. No element should be left out. Here 2 is left out. That is why it is not a function. But in this particular example, 1 is related to A, 2 is related to B and 3 is related to C. That means every element in X is related to some element in Y. That means this could be a function, but then this proper thing to be a function, one more rule has to be fulfilled. The second rule says that every element in X has a unique mapping. That means no two different ordered pairs have the same first component. They shouldn't have the same first component. That means two things cannot be related to the same element. Two items cannot be related to the same element. That is why in this particular example, you can see 1, 2 and 3 all are related to elements in Y, but the problem is that A is related to 1, B is also related to the same element 1. So, two elements are related to 1. Both of them have the same first element. Can you see that? Yes. So that is why, since 1 and A, 1 and B are two ordered pairs where the first component is the same, that is why it is not fulfilling your second rule. That is why this is not a function. Function is represented by this symbol f dot x arrow y. It is read as f is a mapping from x to y, or it is also read as f maps x into y. Okay. For example, x is a set and y is another set. Elements of x are mapped into the elements of y. Now in this example you can see x is mapped into y. That means I will say that y is the image of x. Okay. Y, since x is mapped into y, so I'll say y is the image of x and x is the pre-image of y. Correct? Now when x is mapped into y, it is an image. So this image is also represented as f of x. Correct? It is also represented as f of x. Then I can also say that y is equal to fx. Clear? Yes? Okay. Now, let us take one example. I have set x with elements 1, 2, 3, 4 and I have set y with elements 1, 4, 9, 16 and 25. Now, over here you can see that 1 is mapped into 1, 2 is mapped into 4, 3 is mapped into 9, 4 is mapped into 16 and 25 is left out, right? Every element of x is mapping into some element of y. So I will say that it could be a function. First rule is fulfilled, right? Now every element of x has a unique image in y. Correct? So every ordered pair has a different first component. Can you see that our ordered pairs are 1, 1, 2, 4, 3, 9 and 4, 16. You can see every ordered pair has a different first component. So that is why the second rule is also fulfilled. That is why it is an example of a function. Now in this one, the elements of x that are there is called the domain of the function. Okay, the elements of x is called the domain of the function. The elements of y is called the codomain of the function. X elements are called domain of f. Elements of y are called codomain of f. Now you can see that 1, 4, 9 and 6 are the images of elements of x, right? So if you make a set out of that, the set contains 1, 4, 9 and 16. This set of images of x in y, this set is called the range of f. Clear? Yes? Elements of x are called the domain. The elements of y are called the codomain, and the set of images of x is called the range. Next topic is real valued functions. Now what is a real valued function? A function which has either r or one of its subsets as its range is called a real valued function. Further, if its domain is also either r or a subset of r, then it is called a real function. For example, if f is a mapping from r to r, r is the set of real numbers. F is mapped from the set of real numbers into the set of real numbers, then it is a real valued function. Or you can have any subset of the real numbers, for example natural numbers, rational numbers, whatever you take, then the function will be called a real valued function. Okay. Now domain and range of a real valued function. The set of all real numbers x for which the fx is a real number is called the domain of the real function, and it is denoted by df. The domain of a real function is denoted by df. Okay, and in symbol it is written as df contains all the elements x belonging to R and fx belonging to R. Clear? X belonging to R means on this side you will have R, on this side you have R, and f is a function from R to R. Here all the elements, suppose they are x, okay, in general the element, one of the elements is x, okay, on the other side its image is fx. This x can have many values 1 2 3 4, fx can have many values 1 2 3 4. So when this happens, this set is called the domain of the function and this set is called the codomain of the function, and the set of images of the elements of R is called the range of the function. If this function is a real valued function, then the domain is denoted by df and the range is denoted by rf. Clear? Okay. Now a function doesn't exist if its domain is empty set. Obviously, for a real valued function, there has to be some numbers in the set. There has to be some number in the set. It cannot be empty. Done? Okay. Okay, now this is our core syllabus, that is the type of functions or mapping. There are many types of functions, but out of them we are only discussing one-to-one and onto functions. This is read as one-to-one function. Other name of one-to-one function is injection or injective mapping. Okay, now what is one-to-one function? A mapping or function is said to be one-to-one if different elements of A have different images in B. That means every element of A has got a unique image in B. If this happens, one is related to only one element in B. One element is related to only one element in B. One element is related to only one element in B. No two elements are related to the same image. All of them have only one images. Then this function is called a one-to-one function. For example, look it over here. This element is having this image. this element is having this image and this element is having this image, but no two of them have got the same image. That is why it is called a one-to-one function. In mathematical language, if fx equals to fy, then it should imply that x equals to y. For one-to-one function, this condition must be true. You should start with fx equal to fy and you should be able to reach x equal to y. If this happens, then the given function is a one-to-one function. You could say that this is a condition for one-to-one function. Done? Okay, there is an example over here. See, let A is a set having elements 0, 1, 2, 3 and B is a set having elements -3, -2, -1, 0 and 1, and F is a mapping from A to B defined by fx equal to x minus 3 for all x belonging to A. Show that F is one-to-one. Now the mapping F is defined this way, right? So let me see, F is a mapping from A to B and I know fx equals to x minus 3 and x belongs to the set A, correct? So let me see. In set A, I have got 4 elements 0, 1, 2 and 3. That means my x is either 0, 1, 2 or 3. So let us take them one by one. For x equal to 0, your fx will be 0 minus 3, that is equal to minus 3. For x equal to 1, your fx will be minus 2. For x equal to 2, fx is minus 1. And for x equal to 3, your fx is 0. So in this case, we see that if I map it in the form of a diagram, you can see 0 maps onto minus 3. The image of 0 is minus 3, image of 1 is minus 2, image of 2 is minus 1 and image of 3 is 0. It comes from here. 0 maps to minus 3, 1 maps to minus 2, 2 maps to minus 1 and 3 maps to 0. So accordingly I made the diagram. Over here you can see each element of A has got a different image in B. That is why it is a one-to-one function. Got that? Okay. Now, suppose you are asked to check whether the function is injective or not. Then in that case, how will you check whether a function is injective or not? This is the process for doing it. So see, first what will you do? In the given set, you will take any two elements x and y. Over here in this particular example, you will say let x comma y belong to A. Got that? So take two elements x and y in the domain. That means this is the domain. So in the domain, take x comma y. So I will write let x comma y belongs to A. Got? The next step, find fx and find fy. So your fx will be, I know my fx is x minus 3. So fx will be x minus 3 and find fy. So fy will be f, if in place of x I put a y, fy will be y minus 3. So I got my fx and I got my fy. So what will you do next? You will write the beginning of your condition. Your beginning or your condition begins for one-to-one function at fx equal to fy. So you will write this one, fx equal to fy. Then substitute the values. Your fx is x minus 3 equal to fy is y minus 3. Simplify, go on simplifying until you get in the end x equal to y. If you get x equal to y, your function is one-to-one. If you don't get x equal to y, your function is not one-to-one. The next type of function is onto function. Another name is surjection or surjective mapping. Now, what is an onto function? If every element in B has at least one pre-image in A, then the function is called an onto function or surjection. What is the rule? Every element in B must have at least one pre-image in A. That means every element in B should have one pre-image in A. This side's elements are called images of A. This side's elements are called pre-images of B. Correct? So this is the pre-image side. So elements of B should have at least one pre-image. At least one means one or more than one. That means the elements in B can have more than one pre-image in A. Understanding? The elements in B can have one or more than one pre-image in A. So for here you can see A has the pre-image 1, B has the pre-image 2, C has got two pre-images 3 and 4, D has pre-images 5. So each element of B has got one or more than one pre-image in A. That is why this function is an onto function. Correct? Okay. Now, to find out whether a function is onto or not, you will have to take an arbitrary element y belonging to B. Since the condition talks about the elements of B having pre-images in A, so we will assume an element from B. We'll begin over here. Okay, we'll assume any element y from B. That is why take any element y belonging to B. Then form the equation fx equal to y. Just write fx equal to y. Now fx will be given to you. In place of fx, put the value of fx. Okay, go on simplifying. You will get an equation in terms of x and y. You'll have some x things over here and equal to y. Now what you will do next is solve it to find x in terms of y. This something x equal to y, you will change it, simplify it and write it in the form of x equal to something y. Got that? Make it in terms of x. X in terms of y. X equal to something y, it should come. Got that? Now once you do that, for all y belonging to B, the values of x belonging to A. For y belonging to B, the values of x should belong to A. Right? For y belonging to B, if you put some value in y, the value of x should belong to A. If that happens, then your f is onto. If x doesn't belong to A, then your f is not onto. Clear? Okay, your third type of function is bijective mapping or bijective function or bijection. This is a very important topic. Yes, most of the questions are formed from here. You will get 4 mark or 2 mark questions from this topic. Okay, what is a bijective mapping? A function is said to be bijective if it is both one-to-one and onto. If a function is one-to-one also, onto also, then the function is called a bijective mapping, or it is also called one-to-one correspondence. A bijective mapping is also called one-to-one correspondence. Please keep that in mind. Okay. How do you know that a function is a bijection? For that, you will have to see first whether f is one-to-one. Okay, how do you see f is one-to-one or not? Again, you will write fx equal to fy and try and simplify so that you get to x equal to y. If that happens, it is one-to-one. Second, you'll have to prove that f is onto, because a bijective mapping is one-to-one also, onto also. So find out if f is onto. If both these cases are fulfilled, then your function is a bijection. Let us take one example to see what does it mean. See, let A is a set containing elements 1, 2, 3. B is a set having elements 4, 5 and 6. And F is a mapping from A to B defined by F equals to 1, 4, 2, 5, 3, 6. Now you will have to show that F is a bijective mapping. Now over here your function is given in the form of ordered pairs. That means 1, 2 and 3 are the domain of F. 4, 5 and 6 are the range of F, right? So that means 1, 2 and 3 belongs to the set A, 4, 5, 6 belongs to the set B. So if I form a diagram, your diagram will look like this. 1, 2, 3 and 4, 5, 6. Now you can see in this one, 1 is related to 4, 2 is related to 5 and 3 is related to 6. So in the diagram, 1 maps into 4, 2 maps into 5, 3 maps into 6. So each element of A has a different image in B. So clearly your function is one-to-one. Got it? And at the same time, whether it is onto or not. Now see, for this function to be onto, every element in B must have at least one pre-image in A. You can see F has a pre-image in A. 4 has a pre-image in A, 5 has a pre-image in A, 6 has a pre-image in A. That means the function is also onto. Got that? Now, in this kind of question, sometimes these straightforward functions may not be given. Instead of these things, you may be given an expression. Okay, in that case, how will you find whether your function is onto or not? That is another way of finding. you could check the range and domain of the function. If range of the function is equal to the codomain of the function, then also your f is onto. Okay, first rule, check from the diagram. First method to find whether f is onto, check from the diagram. If you are not able to make the diagram, you can check from here. Second method is range of the function. If it is equal to the codomain, then your function is onto. Okay, if that is also not possible, then go the third way. Third way is by forming that equation. Okay, where you wrote y belongs to b and then you found out fx equal to y, that method. Okay, let us take the second example. Show that the function f defined by fx equal to 2x is 1 to 1 and onto. Now you can see you have to prove that the function is 1 to 1 and onto. That means you'll have to prove that the function is a bijection. For that, see, now your function is given in the form of an expression. Yes, there is no values, no definite elements. It is an expression. So what do? You can take, in the condition it was written, you can take x comma y belong to the set A, isn't it? According to the rule, what was the rule? I had to take, see here, here's your rule. You had to take two random elements x comma y in the domain f, right? Then you had to form fx and you had to form fy, and you had to write fx equal to fy, then move to x equal to y. So we are doing the same thing, but here in place of x comma y, I am taking two elements x1 comma x2 belonging to r. Okay, now since I've taken x1 and x2 belonging to r, I will need fx1 and I'll need fx2, correct? So my fx1 is from here. If I write x1 in place of x, I'll get fx1 equals to 2x1, fx2 equals to 2x2. So I got this one. So begin with my equation. So my equation is fx1 equal to fx2. For 1 to 1, I will check, start from this one, right? So fx1 equals to fx2. But put the value of fx1, 2x1, fx2 is 2x2, 2 gets cancelled. So it implies that x1 is equal to x2. So what am I getting? I started from fx1 equal to fx2. I reached to x1 equal to x2. So the condition of 1 to 1 mapping is being fulfilled. So therefore f is 1 to 1. Okay, now I'll have to prove whether it is onto or not. Now in order to prove whether it is onto, in the range I will have to take an element y, right, in the range, correct? So I'm assuming y belongs to r. Got that? Yes, I'm taking y belonging to r, and then I'm writing fx equal to y according to my condition. Here, according to my condition of onto functions, first step was take an arbitrary element y belonging to b, this second set, right? The image set. From the image set, I took one element y, then I formed the equation fx equal to y, solve it and bring it in terms of x equal to y. Correct? So let me do that. Here I have y belonging to r, then I made fx equal to y. Done. Now I know my fx is equal to 2x. So in place of fx, I am putting 2x equal to y. So write this equation in terms of x equal to something y. I'll have to bring it in this form, right? So x equals to y by 2. Done? Okay. Now, since x belongs to the set of real numbers, whatever value I put in y, whether it be a fraction or 0 or negative number, is always falls into the set of real numbers. That means any value of x belongs to the set of real numbers. So this is true, correct? Now, if this has happened, what is the next step I'll do? I will write fx equals to, calculate the value of fx by putting the value of x here. So fx will be f of my x is y by 2 equals to f of y by 2. F of x is 2x, so f of y by 2 is 2 of y by 2, correct? So from here 2 of y by 2 is 2 and 2 cancelled equals to y. So I'm getting fx equal to y. If you get this, your f is onto. If you don't get fx equal to y, then your f is not onto. So what is the process for finding out whether a function is onto or not? First, suppose y belonging to the codomain side, then write fx equal to y, put the value of fx, simplify, get it in terms of x equal to something y, and then once you get the value of x in terms of y, put that value in fx, simplify, and see whether you get y or not. If you get fx equal to y, your f is onto. If you don't get f is equal to y, your f is not onto. Since in this example f is 1 to 1 also, onto also, therefore f is a bijection. Okay, our next topic is composition of functions or composite functions. Now, let us begin with an example. Suppose you have got set A, you have got set B, and you have got set C. 3 different sets are there. Now, you have F is a mapping from A to B, and G is a mapping from B to C. That means F maps elements of A into B, and G maps the elements of B into C, right? That means these elements are mapped into B, then again these elements are mapped into C. 2 steps of mapping is going on over here, right? Now in composition function, what do is we, instead of going 2 steps, we try to go directly from A to C. We try to join or compose these 2 functions into a single one. Okay, rather than going 2 steps, we take the shortcut and go directly from A to C. When this is done, it is called composition of functions or composite functions. Now we will learn how this is done exactly. Okay, now see here. When x is mapped into B, it becomes fx, correct? And when the element of B is mapped into C, for example, suppose the element of B is y, then if it is mapped into C, it becomes gy, right? But then my y is equal to fx, y is nothing but fx, so instead of y, I can write fx. Got that? Yes, so the element of C can be written as g of fx. Now this is called composition mapping. The sign is this small dot in between G and F. Okay, so look at the definition. Let F be a mapping from A to B and G be a mapping from B to C. Then the composite of F and G is denoted by F composite G is the function F composite G from A to C defined by F composite G of x is equal to g of fx for all x belonging to A. Now this sign shows the composition of 2 mappings into one. Okay, and it is read as, from the right hand side you'll have to start. Do not read it as G composite F, read it as F composite G, because F is done first, then we go on to G. For example here, F is done first, then you go on to G. First F is applied, then only G is applied, right? So that is why it is read as F composite G of x. Now F composite G of x is nothing but G of fx, correct? Okay. Now the composition of functions is also called product function or composite function or resultant of 2 function or simply function of a function. It has got many names, so please mind it. Okay, now there are some properties of composition mapping. Since it is a composition of 2 mappings, we will have to know that this composition of mappings is not commutative. Not commutative means F composite G is not equal to G composite F. These 2 are not same. The value of F composite G may not be the same as the value of G composite F. It is not commutative. Okay, the composition mapping is associative. That means if you have F composite G composite H, it will be equal to F composite G composite H. You can see the brackets have moved. If the bracket moves, it will not make a difference. The values will be same. It will be associative. Okay. Now third condition is that the composition of identity mapping and any other mapping is the mapping itself. For example, see over here. IA is the identity mapping. So IA composite of F is equal to the mapping itself, that is F. This IA vanishes away. IA composite F will give you F. Okay. Similarly, F composite IB will also give you F. Done? Okay. Condition number 4, if F is a mapping from A to B and G is a mapping from B to C, then if F and G are both 1 to 1, F is also 1 to 1, G is also 1 to 1, then F composite G is also 1 to 1. If F is onto and G is onto, then F composite G is also onto. That means that both are 1 to 1 and onto means both this composite of them is also 1 to 1 onto. Or in other words, if F and G are both bijective, F composite G is also bijective. Let us understand composite mapping with the help of an example. Okay, your question is, let the mappings F from A to B and G from B to C be defined as F equals to 1, 2, 3, 5, 4, 1 and G equals to 1, 3, 2, 3 and 5, 1. F is defined this way, G is defined this way. Your task is to find the product mapping F composite G. Product means composition mapping, that is F composite G. Also find the domains and ranges of F and G. That is quite simple, isn't it? So let us begin with the domain and range. From the given condition itself, you can clearly see the first elements are the domain, the second elements are the range. So domain of F is 1, 3 and 4. Range of F is 1, 2 and 5. Right? Similarly, domain of G are the first elements, that is 1, 2 and 5, and range of G are the second elements, that is 1 and 3. Simple? Okay. Now here you can see range of F is the subset of domain of G. Why am I saying this? Because in composition mapping you can see that the range of F and the domain of G fall inside the same set B. Can you see that? Yes. So it could be that some of the elements may be related to B. So I will say that range of F will be related to the domain of G. Correct? So if range of F is a subset of the domain of G, it means F and G are the same. Correct? So that is why we will say that when range of F is a subset of the domain of G, then composition mapping exists. Correct? So since range of F is a subset of the domain of G, therefore F composite G exists. Okay, now for finding out the product mapping. Okay, now in order to find out the product mapping, let us look at the diagram. Now you are given that domain of F is 1, 3 and 4. Domain of F is 1, 3 and 4. That means your set A contains 1, 3 and 4. Next, domain of G is 1, 2 and 5. That means the set B contains 1, 2 and 5. And the third one is range of G is 3 and 1. That means your set C contains 1 and 3. So these are your elements. Okay. Now by looking at the given pairs, I will try to make my diagram. Now F is related as 1, 2, 3, 5, 4, 1. 1, 2, 3, 5, 4, 1, and your G is related as 1, 3, 2, 3, 5, 1. 1, 3, 2, 3, 5, 1. Done? Now these elements are related in this way. Now what is F of 1? F of 1 is 2. From the diagram you can see F of 1 is 2. F of 3 is 5. F of 4 is 1. Similarly, G of 1 is 3. G of 2 is 3. And G of 5 is 1. Got that? Yes. Now, these things could be done without the diagram also. How? See over here. F of 1 is 2. F of 1. If you map 1 you will get the result 2. 1 is mapped into 2, 3 is mapped into 5, 4 is mapped into 1 with the help of function f, right? 1 is mapped into 2, the function f maps 1 into 2, 3 into 5 and 4 into 1. So f1 is 2, f3 is 5, f4 is 1. Similarly, g1 is 3, g2 is 3 and g5 is 1. So from there I got these things. Okay, now your task is to calculate the product mapping F composite G. So how will you get that? See, now by definition your product mapping F composite G is a mapping from A to C given by F composite G is nothing but G of F of X, isn't it? Now here, what is X? What is X? What are the elements? It is F composite G maps A onto C. So what are the elements of A? Your elements of A is 1, 3 and 4. That means by composite mapping, your 1, 3 and 4 are to be mapped into 1 and C, isn't it? So you will have to find F composite G of 1, F composite G of 3 and F composite G of 4. So let us find what are those. So F composite G of 1 is G of F1 according to the definition. Now you know that G of F1 is 2. So in place of F1 put 2, it comes as G2. Now G of 2 is 3. Next, similarly, F composite G of 3 is G of F3 and I know F3 is 5. So G of 5 is 1. Third one, F composite G of 4 is written as G of F4. My F of 4 is 1. So G of 1 is 3. So this way, my F composite G of 1 is 3. F composite G of 3 is 1. And F composite G of 4 is 3. Right? So the mapping F composite G maps 1 into 3, 3 into 1. And 4 into 3, right? So what does my function look like? My function F composite G will be containing, first of all, 1, 3, 3, 1, 4, 3. So you have 1, 3, 3, 1, 4, 3. So this is your required composite mapping.